Welcome, everybody. My name is Arun Gupta. I'm a principal technologist at Amazon. I'm very excited here with my colleague, Jeremy Coben. And today we'll talk about how do you set up a CI/CD pipeline or a deployment pipeline for deploying containers using AWS developer tools. We have our contact information listed on the screen. There are multiple ways to reach out to us. Please feel free to reach out. I saw this tweet from DockerCon 2018, and I think that truly symbolizes the purpose of the CI/CD pipelines. You could try to build your application using microservices, without using any deployment pipelines, but it truly feels like dragging a ship across dry land. It will get you from part A to part B, but think about all the parts that are going to get broken. Think about all the injuries you may occur as going from part A to part B, or point A to point B. You may not even be able to reach from point A to point B if you don't have your set of deployment pipelines correctly. So let's try to understand how at Amazon we have faced the same experience. What I want to do is I want to look back at development processes at Amazon. And when I say look back, I really mean a while back. From 2001 to 2009, Amazon.com, the company itself, has gone through a lot of transformation. Back in 2001, we had monolithic application, one big application that was powering Amazon.com. The teams were all like one big team essentially, but up in 2009, and this is somewhere in between, AWS was launched as well. The Amazon.com application was broken down into multiple small microservices. That's when we also introduced the concept of two-pizza teams. What that means is each microservice is big enough so that it can be fed by two pizzas. There is always debate between customers, American pizza or European pizza, but you know what I mean. A pizza and a team should be able to be fed by those. So the idea is each microservice team essentially is self-contained. They are responsible for creating the service, maintaining the service, operating the service, deploying the service. The QA, the dev, the PM, all of the team is working together. So that's sort of the transformation that we went from 2001 to 2009. Now, one of the leadership principles of Amazon is invent and simplify. And another one is dive deep. So we are always vocally self-critical of ourselves and always looking at it, how we can innovate on customers' behalf. So we looked at, things were doing much better. The models in the teams were releasing faster than ever. So there was always an improvement. But we still felt that things could be better. We could still improve. So in 2009, we ran a study, called as, and you can find this saying, Understanding Amazon's Software Development Process Through Data. And this was in 2009 by John Rosser. We wanted to find out how long it takes to go from code check-in through code being available in production. This included the time it took to build, test, and deploy our software. We learned that this was taking a long time, in the order of weeks, and we didn't want it to take weeks to get a code change out to production. What we did discover was our processes had a lot of human manual work in them, which were taking most of the time. Developers were using tickets or emails to track their release processes. This was the problem we needed to solve. We needed to automate the production line of developer work so that humans, which are sometimes inefficient, were no longer the cause where developers had to wait, when that work could really be automated very easily. So essentially going from writing the code to deploy into production, we wanted to cut down that from weeks and days to really hours and minutes. And that was really the whole essence for the second transformation, so to say. This was important. We could not wait. So we built our own tools. We built our own tools to automate our software release process. Let's take a look what those tools look like. We built deployment pipelines. And this is, again, very internal to Amazon at this point of time, up before 2014. These automated tools would allow you to take your application from development to production very quickly. That's the faster part of it. Because it is scripted, because there is no human error potentially involved into this, it's a lot safer as well. Because the deployment pipelines were a standard language that everybody at Amazon was talking, we could very easily simplify the process because everybody is following the same process, and we could even standardize it as well. And one of the most appealing parts of this deployment pipelines was really the visualization aspect of it, so that you could see how my code is moving across different stages. So this really worked out very well for us. So in 2014, if you look at the landscape of how Amazon.com is now powered, there were thousands of service teams across Amazon. They were all building microservices. Each one of them is really talking to each other using predefined contracts. They were all practicing continuous delivery, which is the habit of taking the code from development through different stages, and we'll talk about those stages in a few minutes, and all the way into production. Another important part of that entire process was how you could take the code not just to production, but you could have multiple stages in between, like staging or beta or production. And then you can test, and then you can see how the code is behaving, and then have multiple environments. So all of this really worked out very well for us. Let's take a look at it, when you're building your microservices, why containers are a good fit. Both microservices and containers, they are enabled to do one thing, only one thing, and really well. So if you look at a microservice, let's say a product microservice, then you will say that this product microservices is exposing HTTP CRUD functions. So my get, put, post, delete. And that's the only thing it's going to do. If you need some other capability about some other, say, people or resource or a cart, then that would be a different microservice. Similarly, if you look at a Docker container, then in that sense, a Docker container can do only one thing. If you look at a Docker file, for example, it could have multiple CMD commands, but it doesn't matter the previous CMD commands. It's only the last CMD command that matters. So in that sense, they both really kind of seem like a good match for each other. One thing and only one thing. If you look at a microservice, the microservices, they really operate with API. That API could be a REST API or any other way by which you operate. But the underlying implementation of the language doesn't matter really. If you could be using Java today, that could be using Node, or if a domain-specific language comes up, it doesn't matter what language you're using as long as you're honoring the API. So that gives you that flexibility. And same thing is with Docker as well. If you're deploying a Docker container, you bring all the dependencies of the language as part of the Docker container itself. So again, microservices and containers, it doesn't matter what app, what language, what framework you are using. One of the biggest issues typically when you're deploying your microservices is the impedance mismatch between your development, test, staging, and production environment. And the reason that occurs is because these are all different environments. And if you're asking to deploying your, say, Java application or Node application or .NET application, then they come with a lot of dependencies. And containers really solve that really well. If you have one Docker image, that becomes your ultimate source of truth. And that is the only artifact that goes from different staging environments. And that's what makes it really compelling, because it really allows you to cut down the impedance mismatch between your different environments. Microservices are self-contained in the sense, if this is a product microservice, it has everything that it needs to serve around product. And so is the case as you package your Docker container as well. Both microservices and Docker containers are isolated execution environment. That is the design of a Docker container, for example, because in this case, Docker containers are built on basic Unix concepts like C groups and namespaces that gives you that isolated execution environment. So if one container goes bad, it cannot inflect another Docker container. Typically, you will deploy microservices in a big cluster of machines, like say EC2 instances. Now, if the microservices need to scale up dynamically or shrink down, you need a faster startup time. You can't really rely upon downloading the entire application or firing up a VM and then installing the stack and then running your microservice. And Docker containers are really good at that. Docker containers can be quickly downloaded depending upon how you have built your image. Once you download the image, then you can fire up the container, and they really complement nicely with microservices. And last but not the least, as your application gets popular, you want the ability to be able to scale up very easily. And you also need the ability to upgrade your application. As you're constantly releasing new versions, you want a new capability to be available to your customers. And so Docker containers enable that very easily, where you can just install a new Docker image and then say, use that for running my next instance of the service. So in that sense, microservices and containers are really a nice match for each other. Now at AWS, let's take a look at it. What do we offer in terms of managed services? Well, of course, we have ECS, which is Elastic Container Service. We launched that service a few years ago, and that service is extremely popular amongst our customers. A few weeks back, we also launched EKS, which is Elastic Container Service for Kubernetes. This is our managed Kubernetes service. As you realize, 57% of Kubernetes for the latest CNCF survey runs on AWS. Now, customers came to us that running Kubernetes is hard, that is undifferentiated heavy lifting for us. Run Kubernetes for us. That's the reason we listened to customer feedback, and that's the reason we created EKS. That's the reason ECS was created, because when ECS was launched, at that time, there were no container orchestration frameworks. Well, of course, you can use ECS or EKS. Now, the idea is that, well, today, we can host these services on EC2, wherein we are using a classic EC2 infrastructure. We are saying, okay, we can provide you a control plane. You bring your worker, and that's your data plane, and you run that worker data plane on EC2. But last year at re:Invent, we also introduced AWS Fargate, which is a new technology, and we'll talk about that in a second, in which case you don't really have to worry about the data plane, because from an application developer perspective, your goal is just to fire up an application, build a Docker image, and run it. Why do you have to worry about the control plane or data plane? So we'll talk about Fargate in a second. And then, of course, we have the Amazon Elastic Container Registry, or ECR, where you can securely save your Docker images and use them as you're building your applications very easily. Now, with ECS particularly, we have seen huge growth in the past few years. There are hundreds of millions of containers that are started each week with millions of container instances. And ECS has been extremely popular with our customer base. So let's take a look at it. If you're using containers, using any of these managed services, how does it look like? Now, at the top, what I'm showing is really the two managed services, so ECS and EKS. On the bottom, typically when you're deploying your application, you would like it to be highly available. So you will deploy in a region that has multiple availability zones. Now in each availability zone, that is where your data plane is, you will set up multiple EC2 instances. On each EC2 instance, you will typically have multiple containers running. So essentially your application is spread across multiple availability zones in a region, and you can have multiple such regions in which your application is available to have a reduced latency return to your customers. So the application could be architected in many ways, but this is one of the ways that you could possibly look at architecting your application. Okay? So if you double click on the instances, it reveals that there is additional supporting software that you need to run, maintain, and patch all your virtual machines, which is the worker nodes, to support your containers. So things like Docker daemon. Now I'm showing this specifically for ECS at this point of time, but there are similar analogies for EKS as well. But essentially what you have is a Docker daemon, you have an ECS agent, and an ECS army. ECS army is the army which is pre-built for and pre-configured for ECS. If you're running Kubernetes, then of course you will have kubelet and Docker agent and similar pre-built Kubernetes armies. On that EC2 instance, of course, you're running your ECS task or your kubelet manifest, which is a pod or a deployment. Now, if you're running this on, if you're looking at a real picture, it looks something like this. Now, there are additional layers of management that you need to be aware of when all you wanted to run containers. That's exactly where we introduced Fargate. Fargate support for ECS enables you to do just that. Fully managed orchestration, as well as data plane experience, bringing your focus to only containers. You still have to create a ECS cluster, which says that, okay, I'm going to create a cluster for administrative purpose, but you don't need to worry about creating your data plane. because you just bring your container and we provision the container for you in that particular ECS cluster. ECS support for Fargate was announced at last year reInvent, and we are working actively with the community to integrate Fargate support for ECS. Now, running Fargate containers with ECS, so you continue to define your application as you do for ECS today and use the same APIs. This is a very important part. You're using the same task definition schema. Running containers as Fargate or EC2 is really a launch time decision. It's not really a build time decision. You can have the exact same task definition deployed on EC2 mode or Fargate mode. There is really no additional plugin to be added to run your containers as Fargate. And because you continue to leverage the same constructs and APIs, not only is your migration between EC2 and Fargate easy, but you can run, so to say, a Fargateized service and one that runs on your EC2 instances side by side within the same cluster. So you get flexibility in picking the launch type for your purpose without breaking the model of co-location of your apps. So it kind of allows you to build a strategy by which you can say, I'm going to start with Fargate-based services, and if I need more control, then I can maybe go to the EC2 launch mode. A little bit more details about how can you right-size your microservices with Fargate. Here are the various configurations supported today with Fargate. As you can see, you can have anywhere from 2 GB per vCPU to generally up to 8 GB per vCPU for various configurations. So I can start from like half megabyte to 2 GB up to 30 GB, and depending upon, there are different CPU and memory configurations that are available for you. You only pay for per second basis with the one minimum. And you can look at the Fargate website for the exact pricing details, but the idea being you get a lot of knobs and levers for you to figure out how can you really right-size your microservices. So you may ask, with Fargate and EC2 launch types available, which one should I pick for workloads? Or if you say that I like the simplicity of Fargate, but when should I think about using the EC2 launch type? How much you want to manage? Do you want to use on-demand or spot instances? Do you have specific memory or compute requirements? The key to understanding is that it is not a one-way door. You can go back and forth as the schemas are compatible, and the administrative boundary is still the same ECS cluster as we mentioned earlier. So Fargate clusters are heterogeneous. Let's take a look at this cluster in this case. So you have different requirements when the notifications app team would like to be moved to Fargate, but has a different timeline planted to do so, but are ready to use Fargate for your shopping cart and web apps. So in this case, I have my web app and shopping cart already into Fargate mode, but my notification, which is my classic app, is still running on the EC2 mode. So you can see how these services are still spread across multiple availability zones, co-located on the ECS cluster, but they're using different launch type modes. So you may say that this is exciting, but how do I start? How do I build a deployment pipeline for creating my microservices using containers? I'm not going to oversimplify this because it is a complex answer. Building deployment pipelines, getting into the microservices journey is not for the faint of the heart. It can require organizational challenges, cultural challenges, process changes. And plus, there is no one right answer for all. It's very personal, very specific to your individual organization. Every company is going to tweak their approach to optimize for their own environment. But you need to still go through the DevOps maturity model and understand where you are in that journey. So let's take a look at it. So now each team release process, if you look at it, essentially, there are multiple stages in it. It takes a different shape to accommodate the needs of each team, but each team still kind of brings it down to 5 stages. So you have source, build, test, deploy, and monitor. Each phase of the process provides increased confidence that the code being made available to customers will work in a way that it was being intended to. So during the source phase, developers check changes into a source code repository. Many teams require peer feedback or code changes before shipping code into production. Some teams use code reviews to provide peer feedback on the quality of code change. Others just use pair programming as a way to provide real-time peer feedback. During the build phase, an application source code is built and the quality of the code is tested on the build machine. The most common type of quality check are automated tests that do not require a server in order to execute and can be initiated from a test harness. So like if you're running a Java application, you can just say Maven test and maybe have a JUnit test integrated over there. The goal of the test phase is to perform tests that cannot be done on during the build phase and require the software to be deployed to a production-like stages. Once these tests include, well, often these tests include testing integration with other live systems, load testing, UI testing, and penetration testing. Finally, code gets deployed to production. Different teams have different deployment strategies, though we all share a goal of reducing risk when deploying new changes and minimizing the impact if a bad change does get out of production. Once in production, we of course want to monitor our code for unusual activity or errors. Each of these steps can be automated without the entire release process being automated, and there are several levels of release automation that I'll step through next. So at AWS, we have developed tools for our customers that are based on our internal tools we use for our process. So we all, in terms of monitoring, we always had like AWS X-Ray and Amazon CloudWatch, which provides you end-to-end tracing for your application, and CloudWatch is where you store your logs typically. On the source side, we have CodeCommit, which is a fully managed source control service that makes it easy for companies to host, secure, and highly scalable private Git repositories. CodeCommit eliminates the need to operate your own source control system or worry about scaling its infrastructure. On the build side, we have AWS CodeBuild, which is again a fully managed build service, very much like other AWS services. It compiles source code, runs tests, produces software packages that are ready to deploy. With CodeBuild, again, you don't need to provision, manage, and scale your own build service. You can use CodeBuild with third-party software for all the testing purposes. And finally, we have AWS CodeDeploy, which is a service that automates software deployments to a variety of compute services, including Amazon EC2, AWS Lambda, and instances running on premises. And the integration of CodeDeploy with containers is a work in progress already. Now, from your perspective, when you are building a deployment pipeline, you may not want to deal with each and every individual piece, and that's where AWS CodePipeline provides an integrated view of all of these tools from your perspective. And we also have AWS CodeStar, where if you are starting a project, then you can say this is an AWS CodeStar project, which not only generates your code commit repos, your code build servers, and your code deploy servers and code pipeline, but it kind of gives you a unified integrated feeling for how all of these tools work with each other. So these are the basic concepts that I wanted to explain, and I would let Jeremy take over from here.
All right, thanks, Arun. So as part of my demonstration today, I'm going to be making use of a service known as AWS Service Catalog. And AWS Service Catalog is a way for IT operations to surface a set of curated templates that developers can use to provision infrastructure without necessarily granting them elevated privileges to create the infrastructure that they need to deploy their services. And there are several benefits that come along with the service catalog. First, IT operations gets a way to standardize the environment through these templates. They also have an opportunity to enforce things like consistency and compliance. They limit access by only allowing certain groups of developers from provisioning certain products that are surfaced through the catalog. And they can enforce things like tagging and security group compliance. Whereas developers can get autonomy to provision infrastructure themselves, the infrastructure that they need to host their services, and they get that speed that they need to deliver innovation quickly through things like automated deployments. Service Catalog consists of 4 major components. There's this concept of a product, which you can think of as a parameterized CloudFormation template, and we'll have a look at that shortly. There's also a portfolio, which consists of a set of products. There are also constraints, which you can place on the parameters that are part of your templates. And then there are provision products that, that users of Service Catalog can use to update or modify products that they've provisioned through Service Catalog. And the way this works is that as an IT administrator or as an operations person, I would first create a set of parameterized templates. I would then publish those to a Service Catalog portfolio. I could then target that portfolio to a group of IAM users or an IAM role. And then an end user, like a developer, would come to the portal. They would be presented with a set of products that were assigned to them, and they would be able to provision those products directly through the Service Catalog console. And so today in my demo, I am going to show you the use of two products. There's a product that I have that creates the foundational infrastructure to run a Fargate service. This includes things like a VPC, security groups, a load balancer, an ECS cluster, although that ECS cluster will have no instances as part of it because we are using Fargate. And then there's a separate Java service template or product that will be used to configure the continuous delivery pipeline. So this is an illustration of the infrastructure that's going to be provisioned. And this is a facsimile of the sort of pipeline that we're going to be creating through Service Catalog. We're going to be creating a Git repository through CodeCommit, which is AWS's Git compatible source code repository. Then we're going to make use of code build to create an asset and then to copy that asset into a Docker image which will then get pushed to ECR and then ultimately deployed to ECS as Fargate task. This is an example of a build spec. When you use code build, you have to supply this file, and in this file consists of multiple stages. In the first stage, I'm installing Maven, which I'm going to use to compile my Java application. And then in the pre-build phase, I'm going to get the build ID, and I'm going to use that to tag my image later. But later in the pre-build phase, you can see that I'm logging into an ECR registry, and then I'm building my Java package. Then in the build phase, I'm building my Docker image and tagging that image. And then finally, in the post-build phase, I push that image to the registry, and I output the image name along with its tag, which I'm going to use for my deployment. Now, well, in the previous example, I explained how you could use CodePipeline to deploy a service to ECS. CodePipeline is a multifaceted service. It not only works with ECS, but it also works with other services like EKS as well as self-managed Kubernetes. And so here's an example of a pipeline that you could potentially create through CodePipeline, very similar to the pipeline that I showed you earlier, except this is making use of AWS Lambda to update a Kubernetes manifest to to deploy the service onto a Kubernetes cluster. So with that, let me end the presentation and show you the demonstration. So here is Service Catalog. I'm logged in as an end user of Service Catalog. And imagine that I'm a developer and I want to I want to start building my service. And so the first thing that I would do is I would come here and I would launch a new product. And I'll give that product a name. I'll call it ECS demo. And I'll select a version, select the latest version. And then you'll see that it's prompting me to enter a name for my code repository. I'm going to call it Red Java. Now, I'm not going to continue through all of the steps that are part of this, but when this is complete, it will have provisioned a VPC with all of the subnets and security groups and so forth to host my service. It will also create a code commit repository that I can begin using to store my code. So let me cancel this and come over here, and I will clone that repository. My machine. Now, while it's doing that, you may be wondering how I knew the location of that repository. When you provision a product, it will appear in the provisions product list, and if you look at the provision product details, you'll see lots of different outputs, including the clone URL of that repository. And so I'm using this to clone that repository, which is ordinarily empty, and then once I have it on my machine, I can then upload or copy my code into that repository and then push my changes to it. So once I'm done with this phase, I would then return to the catalog, and I would provision my Java service next, or the pipeline. So I'd give this a name. And you'll see that it's asking me for a variety of inputs, including the stack name. Now, this is the name of the previous stack that I created in the first step. It's also asking me for a team name along with the service name. I'm going to call it Java. The container port for my service, the amount of CPU and memory I want to assign to it, the desired count, which I'm going to leave at 0 for now. The IAM role that I want to assign to my task, if my task needs permissions to say access an object in an S3 bucket or to write data to a DynamoDB table, I can specify the ARN of that role in this field. The path of the service, this particular service uses the list path, the health check path, ping, and then a priority for the target group rule. Again, I'm not going to complete all the steps necessary to provision this because I've done it earlier, but this will provision that pipeline, and we'll have a look at that here momentarily. But before we do, let me make a change to a file in the repository, or the Git repo that I cloned to my machine. And we'll come over here and we'll change the aircraft type to, say, A380. And then I'll do a git add. And then I'll do a git commit. And then I'll do a git push. And so while that's pushing those changes to my Git repository, let's have a look at the pipeline that the product, that service catalog product created. You can see it consists of 3 steps. There's a source step. This is listening for changes in my Git repository. When such changes occur, it will then trigger a build. The code will be copied to an S3 bucket where code build will pick it up, and then it will be copied into a container that is then used to build my container image. The image is then pushed to an ECR registry, and then finally a task definition and service definition are updated, and that service is then deployed onto ECS. Let's have a look at ECS. You'll see that I have my ECS cluster here, and there are no instances running. However, if I click on the Services tab, you'll see I have that Java service running. If I click on the Java service itself, you can get some additional details about it, such as the subnets that it's allowed to run on, along with the security groups that it's a part of. All of these things were provisioned as part of that CloudFormation template, or that service catalog product that I referred to earlier. You could also see within here the logs. And so in addition to creating that service, I also configured the service to output the logs from the container directly to CloudWatch, and those logs happen to be surfaced through the ECS console. So as a developer, if you have read access to the ECS console, you can look at the logs right from here. And then when the service is finished being deployed, the developer can look at the URL that's outputted from the first template and see the output from the API that they created. So if I come back to the service catalog and we look at the, if we look at the provision product details again, you can see the external URL that is outputted from the template. And so as a developer, I would use this to look at the results of my push and to make any subsequent changes if the results aren't what I expect. So hopefully that gives you an idea of how you could use Service Catalog to automate the creation of your delivery pipelines, and how, as an IT operations person, you can make it easier for developers to quickly get going with their applications. Thank you all for attending today's webinar. Appreciate your attention. If you have questions, please enter those into the chat, and our moderators will be answering them. Thanks again.